Okay, let's start. Who can go first?
I can go first.
Okay, please feel free to share your screen. Okay, you can start.
I think you're muted.
Sorry about that. I just noticed. Yeah, thanks. Hello, everybody. My name's Alex Kiefer. I'm a computer science master's student, primarily specializing in security. A lot of the research that I do is primarily in two groups. The first being with Ari Fulazad, whose specialization is graph neural networks, which is what this presentation today will be about. And then I also work with Greg Lewis and Bennett Burtenthal in the Trusting AI lab, where we're studying how human and computer, particularly AI interaction, can influence the trust of people. Some of my research interests that I also just previously mentioned are graph neural networks, optimizations using sparsity, signal processing, and quantum networks. Okay, so the problem that I'm going to be talking about today is graph neural networks and how we can improve their performance, especially for very large data sets. So graph learning, it's a very active area of research at the moment. I wouldn't say that it's as spectacular as when convolutional neural networks were first introduced with ImageNet, though I would like to think so. But it has applications in logistics, networking, security, bioinformatics, pretty much all fields where you can represent data as graphs. So we've had a lot of advances in this field, particularly on the software side. However, we haven't had that much support for hardware side computations on graphs. For this reason, one of the projects that I thought would be interesting to attack for this is how we can improve that on the hardware. So because a lot of real world graphs are sparse, and even in the case where they aren't sparse but dense, they can be sparsified, you can get a lot of performance improvement specifically by using operations that are sparsified rather than normal dense operations. So what that means is you're going to have a large adjacency matrix where your edges between nodes are represented. And a lot of those entries are going to be zero. And sparse matrices allow you to compress that representation down, and you can do operations in a way which is a lot quicker by ignoring those zero values rather than treating all values as relevant. So why does this matter? Graphs are all around us, so almost every kind of information, or very many kinds of information, can be represented in one way or another using a network or a graph. And because of that, this gives us the opportunity to optimize a general method in that it can be applied in multiple places. So just like we have linear algebra, which backs a lot of software today, graph neural networks and graphs in general back a lot of the data structures that we have today. So if we can optimize this, we can see a performance improvement in a variety of different fields. Now, specifically about graph neural networks, as I previously said, they're somewhat similar to convolutional neural networks. However, they operate on graph data. And I would like to hope that they will have a similar impact on research and industry as CNNs did when ImageNet first came out and kind of sparked the AI revolution. So some example applications for graph neural networks specifically that have been documented in research are antibiotic discovery, physics simulations, fake news detection, traffic prediction, and recommendation systems. So it really spans the whole board of what these are capable of doing. So the solution here that we're trying to aim for is that we can improve the performance of graph neural networks on real world data sets, that being sparse data sets, by using sparse computations at the hardware level. So the specific operation that I'm hoping to implement at the hardware level for this optimization is called SPMM, or sparse matrix dense matrix multiplication. So in this operation, you're taking a sparse matrix and a dense matrix and computing a multiplication between the two matrices. And this is different than, normal dense matrix multiplication, and is optimized and uses less memory and is a lot faster. So this is an example of how that kind of happens. So first you have to, load the registers for the sparse matrix and then the dense matrix, and then you compute the multiplication together. This specific example, I believe, is on a GPU. So the actual implementation in VHDL or something would be a little bit different, but this is the general idea of what's going on in this kind of operation. So for my project, I'm going to primarily be using this paper, which recently came out, called Sextans, streaming accelerator for general purpose sparse matrix dense matrix multiplication, in which they create an accelerator which is based on this overall architecture right here for computing sparse and dense matrix multiplications. I'm very likely going to end up simplifying their architecture and maybe implementing just the one part, the sparse matrix dense matrix multiplications. Mostly because a lot of this, like implementing HBM memory and VHDL, is probably beyond what I'm capable of in 3 weeks. And I would think that even just implementing the sparse matrix multiplication will be a challenge, but more likely to be doable within 3 weeks. So that's kind of the idea that I have for the project. As for the schedule, so the first week I hope to read the paper more in depth and gather a really in-depth understanding of what's going on with the architecture and the underlying implementation, so that I'll be able to implement that in VHDL. During the second week, I'll start implementing that, just writing all the code, making sure that it compiles and everything. And then in that third week, I'm hoping to kind of finalize the VHDL implementation and write some test cases so that we can perform our evaluation of the accelerator. And in terms of the evaluation, this is kind of what I envision as being the two most important metrics. So does the circuit correctly compute sparse matrix dense matrix multiplication? I think that is the bare minimum that I would say I would need to do for this project in order for it to be successful. And the second one, which is more of a, in this case, good to have, does the sparse accelerator provide performance improvement over traditional dense multiplication? In order to do that, I think I would end up having to write more VHDL to compute dense multiplications between matrices and then compare to that. So I don't know if I'll end up having the time to do that, but if I do, that is something that I will try to achieve. These are some additional resources that I have listed for in case, this project doesn't pan out and I need something else to go for. And yes, that's everything. Thank you very much.
First, the graph convolution neural network is at least, is also very important. Maybe even more important than the convolutional neural network. So it's a very ambitious project. I don't expect you can implement all your permits, all you presented here, but you can, if you can deliver a matrix multiplication unit, I'm good with that. It's it deserves A.
Yeah, that's the specific thing that I'm trying to focus on. I mean, I just kind of talked about graph neural networks and everything to put this into context, but the specific thing that I'm trying to implement is that sparse matrix dense matrix multiplication, and not the entire stack for graph neural network computations, because yeah, that definitely is far beyond the scope of what I think would be capable within 3 weeks. So Yeah, just specifically that operation.
Okay. Again, you don't have to finish everything in 3 weeks, but I believe 3 weeks can, make you understand why, whether your original goal is realistic or not. You don't have to finish that within 3 weeks. You have more time.
Okay, yeah, thank you. Yeah, I mean, yeah, this is just the plan. So of course that can be changed, and I have other resources to, fall back on in the case that I don't think that this is possible. But yeah, you're completely correct.
Okay, thank you very much.
Thank you, Professor.
Next one, please.
Me and Jesus can go. Can everyone see our slides?
Yes.
Okay. Our final project is a parallel dot product.
Hi, so I'm Jesus Padillo. I'm an accelerated master's student studying ISE with and concentrating in computer engineering. And most of the stuff that I've done has been in either embedded systems, C, or Python with machine learning and things like that.
Hi, my name is Andre McDowell. I'm an accelerated student in ISE pursuing a specialty in computer engineering.
So the idea or like the motivation for this project is that when computing matrix multiplications, like they're used everywhere, pretty much everywhere in computing, whether it comes to like image processing or anything like that. And usually it takes up time because the matrices are pretty big depending on what the vector and the matrix weights are. So to parallelize that, you could, well, depending on what hardware you have, you could basically use multiple dot products for each row in the matrix with the input vector. And depending on how many cores your computer or whatever your CPU is, then you could divide it up by that to just basically divide up the workflow and save time.
So why is this important? The dot products is the basic method for combining two vectors and giving more information on how two vectors are pointing in the same direction. Dot product is extremely important when it comes to neural networks. By learning how to build a dot product on hardware, we can better be successful at working on neural networks and hardware in the future. A hardware dot product can increase the speed of neural networks because it can parallelize the amount of computations when each core is computed.
So our solution for implementing this dot product, well, first over these first 3 weeks is we're going to see if we can get a floating point unit to work so we can get more accurate matrix multiplications. But if we can't, then we'll just use regular integer, like signed integer values, because of reading and writing to a floating point unit. We'll see. That's like the main goal.
So for this schedule, so we're going to try to do setup between March 28th and March 25th, and then compute the dot product March 1st through April 8th, and then finish up and return data April 8th and through the 18th. And then we have documentation from April 18th through the 29th. But we gave ourselves an extra week in that time during documentation to just make sure that everything goes right. So if something doesn't work in the time frame that we had before, we have some time to catch up. So the evaluation plan, to evaluate the correctness of building the matrix multiplication by n by n matrix, will be passing into test benches along with the n vector values to see if the results are correct. And then to evaluate the feasibility of the floating point computations. That's pretty much it.
Good. This is a very concrete and pragmatic project. Very good. Thank you. Next, please.
We can go. Share my screen.
Okay, I can see it.
Okay.
Okay, our project is a 16-bit CPU. I'm Brian Schwantes, and my partner is Andrew Gotts. We're both in the Intelligent Systems Engineering Accelerated Master's Program. My specialization is cyber physical systems, and Andrew's is computer engineering. So for our project, like I said, we want to design and implement a 16-bit CPU in VHDL with RAM. And for this project, we'll have 5 main components, which is the ALU, the RAM, an input-output handler, an instruction manager, and a program counter. For the CPU, we want the ALU to be capable of various operations mathematically and logically, such as addition, subtraction, and or not XOR. And then the program counter, that component will store the address of the next instruction to be loaded by the instruction manager. And then our instruction manager loads instructions in memory and passes them to the ALU. And the input-output handler is controlled by the instruction manager. And that will handle the reading and writing to memory. And then for our RAM, this will allow for variables and instructions to be stored. We want our RAM to store 16-bit data with 8-bit addresses. And this can read and write data to the CPU.
Yeah, so the importance of our project is that we are hoping to learn more about computer architecture and the CPU fundamentals by applying what we have learned in class. This is kind of going to go over how instructions and data are loaded and stored in memory, and we'll go over how CPUs handle instruction from assembly language. Additionally, we are hoping to also learn more about VHDL through the implementation of the CPU. And then also the main computational component is the ALU. And the ALU is made up of a various amount of logic gates, and we'll also expand on the course material. To test each of the components, we're going to build a series of test benches that we'll be running in the Vivado simulations. Once each of the components of the CPU are built, the goal is to connect them all together and then make another test bench that'll simulate a simple program to kind of make sure everything is working well together. So here's a rough outline of our schedule. The first week, we're going to plan and design all components of the CPU and then begin implementing the ALU. In week 2, we're going to finish implementing all components of the ALU and begin testing it, along with implementing RAM originally. In week 3, we're hoping to finish the ALU and then begin testing the RAM, and then from there begin building other components of the CPU in the weeks that follow. So here's our evaluation plan. We're hoping to successfully implement the ALU during the next 3 weeks to kind of have that benchmark for presentation too. Our project will be evaluated based on the successful implementation of the entire CPU though throughout the course of the project. At the end of the semester, we're gonna try to evaluate the CPU performance time if time permits, and like other factors and performance metrics. And that is it.
Good. This is also very good project. Yeah, I hope you eventually can have that 5-stage pipeline. You don't have to implement a lot of functions in the ALU. Maybe XOR, some logic operation is enough. But I hope you can have that, that pipeline design.
Absolutely.
Will do. Thank you.
Thank you. Next group, please.
Hello everyone. Can you see my screen?
We can see you, but no screen sharing. Yes,
okay.
yes.
Okay.
Good.
I am Isuru Ranavaka. I'm from Masters of Intelligent Systems Engineering. So my project is to implementing a hardware optimized minimal gate recurrent units on FPGA to improve the performance of recurrent neural networks. So basically, the recurrent neural networks, like it uses the temporal data. As you can see in the diagram, we can see that the time stamp, the current time stamp xt, and the previous time stamp and the future time stamp all are taken as input to the network. And in the hidden layers, it shares the weights from the previous hidden layer to the current hidden layer. And likewise, it is keep recurrent data going on, proceed throughout the network layer. So this is used in basically in sequence analysis, language modeling, machine translation, and speech recognition applications. So we can see that when it comes to the hardware level implementation, like CPU and GPU implementations are basically general purpose hardware. So we cannot utilize the maximum bandwidth on those general purpose hardware. So if we can implement a FPGA based recurrent neural network, then we will be able to achieve good performance, and it will be easily customizable based on our use case, and we can get the energy efficiency as well. So according to the current literature, I have seen that there are a lot of LSTM and gated recurrent unit networks that are implemented on the FPGA. So in LSTM, we can see that there are 3 gates: forgot gate, input gate, and output gate. So in the forgot gate controls the previous hidden state, previous cell state, basically, which carries the long memory. And then the input gate controls the current input, the contribution from the current input, and the output gate controls the amount of hidden state that is exposed to the next cell, LSTM cell. So as you can see that here there are a lot of matrix multiplications, and we need to implement 3 gates as well. And there are this hard mode product as well. So this has improved to the gated recurrent unit, which only has 2 gates: update gate and reset gate. So currently the gated recurrent units is being used, and it only has the hidden state, and the hidden state is not controlled through output gate. It is directly exposed to the next cell of the gated recurrent unit. So again, this we can further improve this gated recurrent unit and come up with a minimal gated unit. So this minimal gated unit is proposed in this paper, and it is being cited I think over 200 papers. So here they are only proposing a 1 gate. So they have claimed that it has a low number of learnable parameters, and it has a high convergence rate and a low memory footprint. So I think that we can use this MGU to implement a recurrent neural network on FPGA. So this is what I thought, like we can get a 7 input vector with the 7 time stamps, and we can feed that into a minimal gate and units like this, and we can do a classification problem through this minimal gated unit implementation. So then it comes to VHDL component mapping, like we can identify that there are element-wise multipliers, subtractors and adders, and tanh generator, sigmoid generator. And out of these three components, like we can create an abstract layer for a gate implementation, and then finally to the cell layer. So this is the implementation timeline. So basically, the basic element implementation, I'm planning to complete it in this week, and then the testing of that basic elements, and then we can wire up that basic elements with the gate layer, and then fine tuning. So I'm not sure whether this might not be able to finish up within 3 weeks, but at the end of semester, I will try to finish up the project. For the evaluation, we can use the MINS dataset, and then we can come up with the Python package to compare the accuracy and runtime. And these are the reference papers that I have used for the literature survey. Yeah, thank you.
Thank you. This is also a very ambitious project. I mean, I can accept that you implement only a part of what you have here.
Okay, yeah. So I will try to at least complete the minimal gate and unit layer. So the rest of the thing is wiring up.
Okay, thank you. Next one.
I can go. Can you see my screen?
Yes.
All right, so this is a very basic project that I decided to do because I have no experience with machine learning or anything, but I do want to learn it. And you said that you would accept a project that does not have a hardware component. So my name is Ayushi Raji, and I will be doing this project by myself. I am a master's student here. I'm doing my intelligent systems engineering, and I started last fall. Fall 21. My concentration area is computer engineering, but I also want to learn something about machine learning. So this was a basic project that I found while I was looking for something to do. So yeah, I will be doing this. So hate speech classification is my project. So what is hate speech? We've all experienced hate speech in some form, I guess, when it's maybe bullying could also be a form of hate speech, but I will be concentrating on the hate speech that is found in online forums or chat rooms or in Twitter comments or Facebook comments. So hate speech, when we encounter it, we don't feel very good, and it makes you feel sad about everything. So the first way of building countermeasures against hate speech would be to identify it. So in a survey that was done in January 2020, at least 44% of internet users had experienced some form of online harassment, and 28% of it was severe, like sexual harassment or physical threats. So the first, I would like to identify, build a classifier that will help in classifying a piece of text as hate speech or not. So I literally have no idea about how I'm going to build this, but the first step for me in building this project would be learning about these machine learning models and deep learning models. So the research that I did for this project, I found that a good way to start would be to use some data sets and train your classifier using deep learning models and natural language processing models. So my plan to implement this project would be in the first week, like this week and the next week, I will first try and gather or learn everything about this, and then plan on how I'm going to do it. And then the second week, I will start building my project and probably finish training my model. And then in the third week, I will test it
hopefully I will be able to get this done in 3 weeks. If not, it'll probably be done by the 4th week. So how do I plan on evaluating my model? It will be as simple as seeing if the model is accurately classifying a piece of text as hate speech or not. That's it. Thank you.
Okay, this is also a very good project. Thank you. Next one,
Thank
please.
All right, I can go next. All right, can y'all see my PowerPoint?
Yes.
Awesome. So my name is Nick LaPlante. I am a part-time first-year grad student in ISE with a focus in computer engineering and of mild interest. I did my undergrad work at IU Bloomington as well, where I majored in informatics and dual majored in game development in the media school. That was in 2017. And back then it wasn't even called LUDI yet. So I'm dating myself a little bit there. My project is to recreate the 1973 classic Atari game Space Race. I really wanted a project where it would run on real hardware. I'm taking real input from physical devices and giving output to real physical devices. And I guess I'm leading on my game dev background a little bit. I figured this would be a really fun way of getting some practice with the actual hardware of an FPGA. And Pong gets all the credit. Space Race is the game that Atari released right after Pong. So I figured it's time to give Space Race a little bit of credit here. So why this project? Like I already stated, I really want to actually have a project running on physical hardware. And with this project, I can have a keyboard giving input for the game, and then FPGA out to a monitor. And because it's a 70s arcade game, the core logic and mechanics of the game are relatively simple. So hopefully that'll keep the scope in line a little bit. And it gives me an excuse to mess with 7-segment displays and dip switches and and buttons and all that kind of fun physical stuff. And since I really want this to run on actual hardware, I was looking around in the Xilinx-based RDA7. It's been around a few years. It's a popular kind of hobbyist grade FPGA board. It has more than enough power for what I'm trying to do. I don't have it yet. It's still in the mail, but I did order one. And one advantage of a board like the RDA7 is that it supports the Diligent PMOD peripherals. I got a picture of one there. Basically, Diligent is an online store. They sell lots of FPGA kind of engineering tools and products. And they have these line of peripherals. Basically, they take, Arduino microcontroller, kind of sensors and adapt them to work with FPGA boards. So things like getting FPGA output is made easier with these kinds of extensions, and they're really cheap and they're easy to get. So I have really no experience with FPGAs. So the first week or the first part of the project, or this first part, I'm planning on messing with getting LEDs blinking, using flip-flops to remember button states, and just getting familiar with the physical kind of components and controlling that in VHDL. Same thing with 7-segment displays, just sending some random data to them just to see if I can get it to output what I want. Then, past that, I want to start sending, test patterns over VGA, getting, just again, some test patterns out to the monitor. I plan on using UART to send and receive kind of input data. And luckily, UART's been around a long time, so there's lots of good documentation on kind of how to work with it and do that. And then inside VHDL, get kind of the basic skeleton for the game code. And I've done stuff like, I've done game logic like this in C# and C++. So luckily that part of it's not going to be the issue. It's going to be porting it to VHDL, which will be a little bit of a challenge for me, I think. And then, you know, kind of in the last chunk, near the end of the class, end of the semester, you know, finalizing the outputs over FPGA to actually match what they need to for the game. Finalize controls, get that working. Hopefully get 2-player working, because, you know, Space Race is a 2-player game. You can kind of see the 2 ships there in that image on the right. You know, wrap up the game logic, you know, make sure there's like a win state and a lose state. You know, the player can, you know, they can die, reset the game, and they can, you know, have their score go up as they win. And then, of course, final kind of testing and debugging, because I'm sure there's going to be several bugs. And then, yeah, again, here's just a general overview of, you know, kind of what my chunks are going to be. So this first chunk, just I/O experimentation and getting familiar with the basics of hardware usage with VHDL. And evaluation is going to be fairly straightforward. You know, does the game crash? Can the player, you know, actually die or win? Does the keyboard give input? You know, so these kinds of basic things. You know, basically, does my VHDL version match the kind of the original Atari one from the 70s? And that is my presentation.
Good. This is also a very ambitious work. So I don't expect you can finish all these points, but I believe that will be a very great project.
Awesome, thank you.
So if you guys have any question, please email me, and I will also email you to update our schedule. Thank you. And then if no more question, we can stop today. Thank you very much.
I have a quick question.
Yes.
So so my partner turned in my PowerPoint last week, but I wasn't able to turn it in.
It doesn't matter. It doesn't matter.
Okay, I just wanted to make sure.
Okay, no problem. Thank you.